This video focuses on the Otto and diesel cycles, two special cycles used in engineering devices for transportation and energy generation. In this video, we start with the Otto cycle first, moving in the second part of the video to the diesel cycle. Otto and diesel cycles are direct cycles because the transformations composing the cycle follow clockwise. Let us understand first some of the basic common engineering aspects of the engines that exploit the Otto and diesel cycles, along with some differences.
Internal combustion engines are thermal engines following the Otto or diesel cycle in an assembly composed in its essential parts by a piston sliding in a cylinder. However, the piston cylinder assembly has a number of additional details and elements beyond the simple piston and the cylinder that are part of the assembly design and are decisive to the engine efficiency. These are the stroke length, the full travel of the piston along the cylinder between the bottom dead center and the top dead center, the crank on the crankshaft together with the connecting rods determines the stroke length, and the bore, the diameter of the cylinder. Stroke length and bore make the displacement volume. The fuel enters the cylinder from an intake valve. After decombustion, the products of the combustion leave the cylinder from the exhaust valve. There is a gap between the top dead center and the cylinder ceiling. The volume in this gap is called the clearance volume and allow the intake and exhaust valves to move up and down without damage the cylinder top. Let us now see how the piston cylinder assembly can be used to perform an Otto or a diesel cycle. We start from the Otto cycle first. The Otto cycle is an approximation of thermodynamic transformations performed in a spark ignition internal combustion engine. We say internal combustion because the fuel combustion happens in the inner of the cylinder. A spark ignition internal combustion engine uses the piston cylinder assembly with the addition of a spark plug. The spark plug starts the fuel reaction through an electric spark localized at the top of the cylinder. A small electrical arc at the plug, along with the compression of the gas mixture through the piston, create the right conditions of temperature and pressure to initiate the combustion of the whole amount of fuel. A spark ignition internal combustion engine goes through 4 steps. In the first step, the cylinder is at the bottom dead center position. The cylinder is full of the air-fuel mixture and is moving upward to compress the reacting mixture. A number of fuels can be used in a spark ignition internal combustion engine, thanks to the possibility to set the optimal condition of temperature and pressure through the piston and the spark. Petrol, methanol and ethanol are among the fuels that can be used in spark ignition internal combustion engines. Air is also present in a cylinder to carry the right amount of oxygen necessary to the combustion. In the second step, the cylinder is at the top dead center and expands due to the combustion reaction, which is initiated by the spark plug. In this step, work is produced. In the third step, the exhaust valve is open and exhaust gases go expelled. Here, work has to be done on the system to move the cylinder up and wash the chamber. The inertia of the cylinder is enough to allow the cylinder to move up. In thermodynamic terms, part of the work previously produced in the expansion is now used for decompression. The fourth step is the intake. The intake valve is opened to allow the suction of the fuel-air mixture. The mixture is made up in the intake duct through an injector that sprays the fuel in the air stream at optimal fuel-air ratios. The piston travels 4 stroke lengths and the crankshafts 2 rounds to complete a cycle. This gives to this configuration of spark ignition engine the name of 4-stroke internal combustion engine. Let us represent the steps described in a PV diagram. The PV diagram is the most suitable to visualize the evolution of the cycle, because this system is characterized by variations of pressure and volume. During compression in step 1, the volume is reduced from the bottom dead center to a value close to top dead center. The transformation can be assumed adiabatic, since the heat losses with the surroundings can be neglected. The spark plug ignites the reaction slightly before reaching the top dead center. A sudden increase of pressure at almost constant volume happens. At the end of the combustion, we observe a small increase of the pressure in the cylinder while it is expanding. This is because of the confinement of the reaction products in a volume which was previously occupied by air and fuel. The expansion continues until a volume close to the bottom dead center, when the exhaust valve opens to let the cylinder get rid of the exhaust. This happens at pressure proximal to ambient. Finally, the exhaust valve closes. The intake valve opens to let the air-fuel mixture enter the cylinder. This obviously happens at pressure lower than the ambient, to have a suction of the mixture. The spark ignition internal combustion engine is not exactly a closed system, since there are times during which the system is closed and times when it is open. We can identify the zone above the ambient pressure in which the system can be approximated as a closed system, and the zone below the ambient pressure in which the system is open. The cycle we are seeing here is called the indicated cycle. It is called indicated since it is indicated by pressure and displacement sensors. The indicated cycle shows the real evolution of pressure and volume of the system. However, a very useful alternative to the indicated cycle is an approximated version of it, which is still representative enough and useful to first understand what is happening in this system in a simple manner. In other words, describe the system and the interrelation among the physical and design variables of the system. Second, come up with indication on how to make the engine more efficient. The simplest thermodynamic approximation of the indicated cycle in a spark ignition internal combustion engine is the Otto cycle. Let us see how it is made. The Otto cycle is a simple representation of the indicated cycle, but descriptive enough of the reality. The approach which leads to the Otto cycle is called Air-Standard approach. In the Air-Standard approach, pure air is the working fluid in the assembly, and the piston cylinder assembly is closed. No valves are present. The expansion, in which the heat of reaction heats up the system, is replaced by indirect heating from an external heat source. The discharge of the fluid and the intake of new fluid is instead represented as a cooling of the air. Heating and cooling happen at constant volume to mimic the almost vertical parts of the indicated cycles in between ignition and end of combustion, and after the exhaust valve opens. The Air-Standard approach assumes that the cycle is internally reversible and operates at steady state. Despite air is in reality a mixture of gases, here air is considered as a pseudo-single fluid. Air is assumed as an ideal gas, and all properties of air are assumed constant as standard conditions. In particular, Cp and Cv are assumed constant across temperature and pressures. Under these assumptions, the upper part of the indicated cycle is approximated by the Otto Air-Standard cycle that is composed by two isocores and two reversible and adiabatic transformations. Now that we have a simple representation of the spark ignition engine according to the Otto Air-Standard cycle, we can easily calculate its efficiency. The objective is to come to two simple expressions for the efficiency. The first expression is only function of temperatures, and in particular the temperatures at the beginning and at the end of the compression. The second expression is a function of the ratio between the top dead center and the bottom dead center volumes, the compression ratio, along with the ratio between Cp and Cv as a parameter. The first expression involves two of the cycle temperatures. Therefore, it is an expression of the efficiency which relates to operating parameters. In other words, parameters that have to do with the way the engine operates. The second expression has to do with volumes, which are instead design parameters. In other words, parameters that are decided at the design stage, before the engine is operated, to produce an engine that is able to realize certain performance. Let us see how to obtain these two expressions from the cycle analysis. The objective is to show that the efficiency of the Otto cycle is according to the identities in the red box. We assume internal reversibility and steady state. We have only air in the cycle. Air is an ideal gas. All the thermodynamic properties of air are constant at the standard conditions of 273.15 Kelvin and 10 to the power of 5 Pascal. Cp and Cv are constant. We remind the cycle in the PV diagram and number the states. The Otto cycle is composed by two isocores and two isentropic transformations. The cycle moves from the top dead center to the bottom dead center. The cycle exchanges heat, Q in the transformation 1-2 and Q out in the transformation 4-1. We want to calculate the efficiency, which is the energy produced over the energy consumed, so the net work over the heat absorbed. The net work is equivalent to the net heat because the variation of internal energy is null in a cycle. The net heat is the difference between Q in and Q out, with the Q in being Q23 and the Q out being Q41. Q41, for an ideal gas that has constant Cv, is just Cv times the variation of temperature between state 4 and state 1. Similarly for Q23. We end up with an expression which is only function of temperatures. We work out the expression in order to write it only as a function of temperature ratios. Now we define the compression ratio as the ratio between the specific volume of the cycle, and in particular the maximum volume when the cylinder is at the bottom dead center, and the minimum volume when the cylinder is at the top dead center. We remember the correlation developed for an ideal gas and adiabatic transformation. This correlation is applicable to the points 1, 2, 3, and 4, since all of them belong to adiabatics. Let us write it for the transformation 3, 4 first. We develop this further and see that the ratio between T3 and T4 is the compression ratio to the power of K minus 1. We can do the same for the transformation 1-2. Therefore, the two temperature ratios can be equated and manipulated. We see that the last term of the expression for the efficiency is equivalent to 1. By remembering the equivalence between temperature ratio and compression ratio, we find the expression we were looking for. When we plot the efficiency against the compression ratio, we see that we need to maximize the compression ratio if we want a high efficiency engine. To do that, we need to design engines with minimum clearance volume and maximum displacement volume. Unfortunately, this technology cannot go beyond compression ratio 10. Beyond compression ratio 10, the temperatures in the cylinder would be so high to let the fuel-air mixture to auto-ignite before the spark. This causes explosions and vibrations, threatening the life of the engine. At compression ratio 10, the Otto Air-Standard cycle shows efficiency of 0.6, but in reality the efficiency of the indicated cycle decreases down in the range from 0.25 to 0.35. An alternative to spark ignition internal combustion engines are the compression ignition internal combustion engines. The diesel cycle is a multi-thermal cycle that approximates the transformations happening in a compression ignition internal combustion engine. We see here how a compression ignition internal combustion engine works first, and then move to the diesel cycle. As in the spark ignition engine, the compression ignition engine uses the piston cylinder assembly. In the compression ignition internal combustion engine, the fuel injector replaces the spark plug. The injector sprays the fuel directly inside the cylinder. To ignite, the fuel doesn't need, in this case, the spark. The fuel used is in this case diesel fuel that is capable to auto-ignite when a certain level of pressure is achieved. The rest of the process remains essentially identical to a spark ignition internal combustion engine. The first step consists of a compression of only air until the piston reaches a predetermined position towards the end of the compression, at which the diesel fuel is sprayed. The spraying is performed before achieving the maximum compression, because the fuel combusts slower than fuels for spark ignition engines. Therefore, before reaching step 2, the fuel is injected in the cylinder. The high temperature and pressure achieved during the compression ignites the fuel-air mixture and moves the piston until the bottom dead center. Finally, the exhaust gases are released and new air sucked in the same way it happens in a spark ignition engine. Also in this case, the piston travels 4 stroke lengths to complete a cycle. Therefore, this engine is also called 4-stroke compression ignition engine. When we overlap the two indicated cycles for spark ignition and compression ignition, we spot identities or similarity for most of the states except at higher cycle pressure, in which the compression ignition achieves significantly higher values of pressure and temperatures. A compression ignition internal combustion engine does not have issues with auto ignition, since most of the compression uses only air. This results in higher compression ratios than a spark ignition engine, leading often to higher efficiency. The diesel cycle is a simple representation of the indicated cycle performed in a compression ignition cycle. The approximation is simple but descriptive enough of the reality. We apply also in this case the Air-Standard approach under the same assumptions already discussed for the Otto cycle. In the Air-Standard approach, pure air is the working fluid in the assembly, and the cylinder piston assembly is closed. No valves are present. The expansion is replaced by indirect heating from an external heat source. The discharge of the fluid and intake of new fluid is instead represented as a cooling of the air. Heating happens at constant pressure with an horizontal segment in the PV diagram. In the indicated diagram, at high pressures, the wide region in which the volume changes due to the combustion is approximated by a constant pressure transformation. The cooling happens instead at constant volume, like in the Otto cycle, since compression ignition and spark ignition engines behave alike at the pressure closer to ambient. The final cycle obtained is called diesel Air-Standard cycle. Therefore, the diesel Air-Standard cycle is composed by one isobar, one isochore, and two reversible and adiabatic transformations, isentropic transformations. This approximates the indicated cycle in the upper region above the ambient pressure. Now that we have a simple representation of the diesel Air-Standard cycle, we can easily calculate its efficiency. The efficiency of the diesel Air-Standard cycle recalls the efficiency of an Otto cycle having the compression ratio multiplied for a factor greater than 1. This factor depends on a second ratio between volumes, R. R is the ratio between the specific volume of the fluid at the end of the isobar transformation and the largest volume in the cycle, the specific volume at the bottom dead center. K is the ratio between Cp and Cv. This expression for the efficiency shows that the theoretical efficiency of the diesel Air-Standard cycle is lower than the efficiency of a corresponding Otto cycle working with the same compression ratio. However, in practice, since the compression ratios technically achievable in compression ignition engines are higher than in spark ignition engines, compression ignition engines usually show higher practical efficiency. Let us see now how the efficiency of the diesel Air-Standard cycle is obtained. We want to obtain the following relation where ρ is the compression ratio, the ratio between maximum and minimum volume, R is the cutoff ratio, the ratio between the volume at the end of combustion and the minimum volume, K is the ratio between Cp and Cv. We use the Air-Standard assumptions identically to the Otto cycle. The diesel cycle is composed by two adiabatics, one isobar and one isochore. Let us number the 4 states of the cycle and mark the 3 important volumes that appear in the expression of the efficiency. In this cycle, heat is transferred in the transformation 2-3 and 4-1. The efficiency can be reduced to a ratio of heats, the net heat over the heat absorbed, and further to 1 minus Q41 over Q23. Q41 is work plus variation of the internal energy, but this transformation is a constant volume, therefore flow work is 0. In an ideal gas with Cv constant, according to the assumption, Q41 is Cv times the variation of temperature between state 4 and state 1. In Q23, the pressure changes and flow work plus variation of internal energy is enthalpy by definition. In ideal gases, the variation of enthalpy is only function of temperature. By assuming Cp constant across the temperature change, Q23 is Cp times T3 minus T2. We develop what we have just obtained now. The aim is to have an expression of the efficiency which is only function of temperature ratios. In this last expression, we have 3 temperature ratios. Let us develop them further. The ratio T2 over T1 follows the same considerations for the Otto cycle. For the ratio T3 over T2, we can write the ideal gas equation of state on the state 3. Since state 2 is at the same pressure of state 3, we can write an equivalence between the ratio T3 over T2 and V3 over V2. We see that the ratio V3 over V2 is the cutoff ratio defined at the beginning. We move now to the last ratio T4 over T1 and start by recalling the equivalence for an adiabatic transformation of an ideal gas for state 4 and state 3. We develop it further. The ratio between the temperatures 4 and 3 is ultimately equivalent to the ratio between the cutoff ratio and the compression ratio to the power of k minus 1. We substitute T3 by using the expression previously found as the product between the cutoff ratio and T2. Then we substitute T2 with the product between T1 and the compression ratio to the power of k minus 1. The final expression for the ratio T4 over T1 simplifies to the cutoff ratio to the power of k. If we plug all these expressions of the temperature ratios in the last expression obtained for the efficiency, we obtain the sought relation. You now know what a spark ignition and compression ignition internal combustion engines are, and their indicated cycles. You know the assumptions of the Air-Standard approach and its usefulness for giving simple correlations to inform the design of practical internal combustion engines. You know how the Otto and diesel Air-Standard cycles approximate the thermodynamic transformations in spark ignition and combustion ignition internal combustion engines. Finally, you can calculate the efficiency of Otto and diesel Air-Standard cycles.